This is Ethan Hansen of the Southern California News Group. I just want to wish everybody a happy college football Saturday. Dodgers game got postponed, but anyway, I am going to help myself study and do a hypothesis test and try to prove that there are more blue M&Ms within 3 bags of an entire M&Ms than there are red M&Ms. And hopefully by doing this video, it'll help other people that are trying to figure out stats how to do it, and this is a good study method for me, so stay tuned. 1 cup 2 and cup 3, and I'm going to pour the M&Ms into these cups and then try to get an N value, an N1 value, and an N2 value, and then my P1 is going to be blue M&Ms, and my P2 is going to be red M&Ms. So P1 blue M&Ms, P2 red M&Ms. First cup that we did, we got a total of 5 blue M&Ms and a total of 5 red M&Ms. Not to be mistaken, but there's a lot of orange M&Ms, and I'm not sure why. But so our first P's are going to be both 5 and 5, and the total is 49, and we'll eventually add those up and divide them up later, but we're just going to continue to do the problem. So we got 5 for blue, 5 for red, and then somebody just decided, well, it's Halloween season, why not put in a bunch of orange? For bag number 2, we got a huge, big thing of orange M&Ms. Why is that? I'm guessing it's got something to do with Halloween, but a little strange to me that a bag of crispy M&Ms would have so much orange in it. But meanwhile, we've got our blue and we've got our red. So now to add up the blues and the reds. So there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wow. Still the same through bag 2. And we will get an even bigger N value. Last time we had 49 M&Ms, and yeah, we'll add that up. Now we finally have some separation with a whopping bit of 21 M&Ms for red and 15 M&Ms for blue. Now because we had some broken M&Ms, we got a little bit of a lower N value than expected. The first N value was 49, the second one was 46, and then we came up in the third bag with only 39. But there was 10 more added for the red and only 4 more added for the blue. So now we're about to put these M&Ms away, and we're about to do a confidence interval and a hypothesis test, and I'm going to show you how to do both. The math part. So for P1, for the blue M&Ms, we got a sample size of 15, and for the red M&Ms, we got a sample size of 21. Now, because we were using the same amount of because of the fact that we were using the same population of M&Ms, the population proportion is going to be the same. So what we're going to do is we're going to add up 49, 46, and 39, and then what we're going to do is we're going to come up with P1 hat and P2 hat by dividing the successes divided by the population proportion, or excuse me, the acceptance versus the successes divided by the failures, or the sample proportion divided by the population proportion. So that's what we're about to do here. Sorry, I had a little bit of a 10-second brain fart, but here we go. The math part. So for P1, for the blue M&Ms, we got a sample size of 15, and for the red M&Ms, we got a sample size of 21. Now, because we were using the same amount of Now, because of the fact that we were using the same population of M&Ms, the population proportion is going to be the same. So what we're going to do is we're going to add up 49, 46, and 39, and then what we're going to do is we're going to come up with P1 hat and P2 hat by dividing the successes divided by the population proportion, or excuse me, the acceptance versus the successes divided by the failures, or the sample proportion divided by the population proportion. So that's what we're about to do here. Sorry, I had a little bit of a 10-second brain fart, but here we go. N1 and N2, what we're going to do is we're going to add up all the populations that we did from the M&Ms, and that's how we're going to get it. So I'm going to take you through it right now. So first, our first population had 49 M&Ms plus 46 M&Ms plus, because of all the wreckage from the third bag, 39 M&Ms, and we come up with a grand total of 134. So that is our number. To come up with our P hat is we're going to divide 15 into 134 and 21 into 134. So here we go. 15 by 134 equals 11.1119, and because we want to round it to the nearest thousandth, we want to eventually round that up into 0.112. So P1 will be 0.112. P2, what we're going to do is we're going to divide 21 into 134. So here we go, 21 divided into 134, and that equals 1.567. So once again, because we want to round up, at P2 will be 0.157. That's ready in minutes. So P1 will be 0.112 and P2 will be 0.157. Problem, we have to do the period of, we have to find the normal criteria. As my professor Scott Macaron once said, it's about going over 10 to pass go. If the p-value times the population proportion is less than 10, then we cannot pass go. We do not collect $200, and therefore we cannot do the problem. So this is how we do it when comparing two population proportions. You do P1. Whoa, looks a little weird on. You do P1 times N1, and then N1 times 1 minus P1, and then P2 times N2, then N2 over 1 minus P2. So, in order for us to do the problem, the normal criteria has to be met, and we will find out if they are met. So we're going to take our P1 value, which is 0.112. My terrible writing. Alright, so we're going to take 0.112. Then we're going to multiply it by 134. Then 134 over 1 minus 112. So, let's see what happens when we add up, when we compute those answers. So, 2 times 134, excuse me, 112 times 134, close, so therefore you get, so that's over 10, so that marks off 1, and now 134 times 1 minus 0.112, that equals 118. So we're good there. Do the normality criteria for part 2, which is P2 hat. So we're gonna go. We're gonna go 0.157 over 134. Then 134 over 1 minus 0.157. If these two are greater than 10, which for these ones we proved that they were greater than 10. The first answer came out to 13. The second one came out to 118. So now we'll do it on the calculator once again, and make sure to always close up the parentheses. So 0.157 times 134 equals 21. Alright, so we're good there. Then 134 over 1 minus 0.157 should be greater than 10, and it is. Alright, so we have just completed the period. We just completed normality criteria. All these came out over 1, over 10. This number came out over 10. This number was 28. This number was 21. This one came out to 112.96. The criterias for normality are met. So now we can move on to doing the hypothesis test, which we will do trying to find a confidence, and doing a confidence interval. So now what we're going to do is we're going to find the standard error. We know that the criteria for normality has been met. And so before we do anything, though, this is the one thing that I like to do, is first of all we have to find the mean of differences. The way you do that is by taking your p hat, which is 0.112, and subtracting it by 1.157, because we're eventually going to have to use these numbers later on. So, once again, 0.112 minus 1.157, that equals negative 0.045. So just when you're doing stats, you just gotta take everything step by step, piece by piece. It's a little long, just like this video that I'm trying to do, but really this isn't for your viewing pleasure as much it is mine. There's nothing witty or humor about this. However, I'll give you a little clip of USC, and damn, that's a nice tackle. All you wahoos, so I am back. So this is what we are going to do. Since we are comparing two since we're comparing two sample proportions, what we're going to have to do is we're going to have to find the pooled proportion. So that means that we're going to have to add up all of our successes or all of our M&Ms and then divide it by all the M&Ms that we counted in general, including those wacky orange ones, which I'm still trying to figure out why there's so much orange in those M&Ms. So in order to find the pooled proportion, we're going to add up 15 and 21 and then divide whatever the answer is for 134 plus 134. So here we go. So it's the successes divided by the amount of tries, or the sample proportion divided by the entire population. So So 15.
Yeah, I love coming up here because it is beautiful.
Yeah, 15 plus
it helps put things into perspective.
21
From my point of view,
by 134. Oh, excuse me. Hold up, I made a mistake. No, you're good. So when you make a mistake like me, just do this. For parentheses, and then 134 plus 134. Put the parentheses over, separate them, and we come out with a grand total of 134. And that is what we are going to use to find our standard error. So 134. Put it right here, and also just to make sure that you're following the steps, be sure to do all your problems. Make sure to do all the steps on a scratch piece of paper. So I'm going to write it down again. So 15 plus 21. I'll just add that up, which would equal 36. 134 plus 134 equals 268 by 36 into 268, and there you go. So that is our pooled proportion right there. Found the pooled proportions. What we need to do now is find the standard error, and the way that we do that is by taking the square root and then taking the pooled proportion, which some people like to call P cubed, P whatever. I like to call it P Ninja because, you know what, P Ninja just sounds a lot cooler than anything my awesome Professor Sam Macaron can come up with it. So P Ninja, and then subtract that by the n value, which is going to be 134. Again, we're going to add it, and then take P Ninja again. Do not do what I just did there. In fact, I'm going to erase that. Put the bracket next to it. 1 minus P Ninja over 134. Now, usually when doing a hypothesis test, you're going to have two different n values. However, because we are dealing with the same number of M&Ms all in one jar, that's just the way it played out. But just know that when you're doing the sample proportion for two different values, when you're doing the standard error for two different values, you're going to come up most likely with different ends. But that's the way we are. So we're going to show you right here, and now we're going to show you how it translates to this amazing tool, the TI-84 calculator. And interestingly enough, too, the p-value is almost the same as, excuse me, the p-ninja is almost the same as 134. But anyway, so what we're going to do now is we're going to go second. See that? So I hit second. And in order to make that a square root, you need to hit x2. So I'm going to hit x2. Then we're going to go p-ninja, which is 0.134 over 1. Excuse me, sorry. That's a bad angle. There you go. Minus over 1. I mean, excuse me. 1 minus 0.134. Oh, excuse me. Just go backward there. 134. And then we're going to divide it. And then we're going to divide that by 134, which, because it just came out, interestingly enough, just like that. So 134, and then we're going to add some game credit bracket. That way we do our PEMDAS, the order of operations. So 1. Excuse me. Excuse me. Here we go. Yeah, so 0.134 over 1 minus 0.134. There we go. We've done all the work. And our standard error is going to come out to be Hold up. Yeah, so 0.34. So that is going to be our standard error. So our standard error came out to be 0.341. So that is our standard error. Next, we're going to find the z-score, which is what I'm going to show you next. Standard error. Now what we're going to do is we're going to find the z-score. So as my professor, the Ninja Master himself, Scott Macaron, said, that when you're dealing with not p-hat, not p1 minus p2, but when you're dealing with the population proportion of p1 minus p2, that is going to equal to 0. So remember, you got to make that separation between p1 hat minus p2 hat and p1 minus p2. p1 hat and p2 hat are your sample proportions, and p1 and minus p2, those are your population proportions. Because those are going to cancel each other out and equal to 0, the way the problem is going to look out. And once again, as we showed you before, that's our answer that we came up with. We already did the hard work of doing p1 minus p2, the sample proportion for the blue M&Ms minus the sample proportion for the red M&Ms. So we go p1 minus p2 hat over p1 minus p2. Since these guys equal 0, you're left with p1 hat minus p2 hat, and what do you know? We already did it right here. So we came up with a value of negative 12 minus 0.157. That equals negative 0.045, and now we got to divide that by our standard error, which came out to be 0.341. So now we're going to take that from right here and do it on the calculator. So here we go. We're going to clear everything and then go negative 0.045 divided by 0.341. That equals -131. And now what we're going to do is we're going to find our p-value. And now our p-value is going to be the area. So the area, which is going to determine whether or not this is going to be statistically significant. Now we chose to say that, oh, this is going to be at a 95% confidence level. So that means that our alpha is 5%. If it's under 5%, that means that the value is statistically significant. We reject the null in favor of the alternative. It means that our hypothesis is indeed correct, and yeah, we get all that money and all that cheese that Professor Macaron is making in the stock market. But we won't be like Professor Macaron if our p-value, if our p-value is over alpha. So if it's over 5%, then we fail to reject the null hypothesis. We do not choose the alternative, and therefore we just know that our hypothesis test was incorrect, which is not to say that it is necessarily incorrect. We just found out that, oh, there's probably going to be more red M&Ms than there are blue M&Ms. So, with all that, first, and also got to be sure to put that answer. And because I said greater than, now we're going to have to take it to normal CDF, and that's what we're going to show you now. Show you how to find the p-value. So what you're going to do is you're going to go to second, and you're going to go to vars, and then you're going to go to normal CDF. Now usually when we're dealing with a negative z-score, you're going to go to -10. However, in the problem, which I created for myself, saying that the proportion was greater than, therefore it's going to be a right tail test. So don't just automatically assume that just because you come up with a negative z value means that your p-value is going to be negative as well. So without further ado, here we go. So you got to use the smaller number first, which is -0.131 over 10. So you're basically taking that number and you're multiplying it 10 times to come up with an answer of 0.552, which is obviously greater, which the p-value now is obviously greater than our alpha. So our alpha is 5%, and our p-value is 55%. So what we do is we fail to reject the null hypothesis, which null also means HO. So, because our p-value was greater than the alpha, we failed to reject the null hypothesis. There are actually more red M&Ms, we proved, than there are blue M&Ms. Our hypothesis test did not fail as much. It was just, well, we proved that one thing is greater than the other. It wasn't my hypothesis test. And that last thing that we need to do now is we need to interpret it, which is an important part of the test. And I'm going to show you that right now.